Welcome to Real Analysis Basics B3, Monotone Sequences and Subsequences. Today, order will force some sequences to converge, while subsequences will give us an efficient way to prove that other sequences do not. Apparently, studying a sequence becomes easier after we selectively ignore most of its terms. Mathematics has excellent public relations. A sequence an is increasing if an plus 1 is at least an for every n. It is decreasing if an plus 1 is at most an for every n. Here, increasing and decreasing allow equality. If every inequality is strict, we say strictly increasing or strictly decreasing. A sequence is monotone if it is either increasing or decreasing. For example, 1 minus 1 over n is increasing and converges to 1. 1 over n is decreasing and converges to 0. But negative 1 to the power n alternates forever. So it is not monotone. Recall that an is bounded above if one real number m lies above every term, and bounded below if one real number m lies below every term. Monotonicity alone does not imply convergence. The sequence an equals n is increasing with great enthusiasm and no intention of approaching a real number. The monotone convergence theorem says that every increasing real sequence bounded above converges. Dually, every decreasing real sequence bounded below converges. In the increasing case, the limit is the supremum of the set of terms, so completeness is about to do actual work. Let A be the set of all terms of the sequence. It is non-empty and bounded above, so the least upper bound property gives a real number L equal to its supremum. Fix epsilon greater than 0. Since L is the least upper bound, L minus epsilon cannot still be an upper bound. Therefore, some term an is greater than L minus epsilon. Now take n at least n. Monotonicity gives an at most an, and L is an upper bound, so an is at most L. Thus L minus epsilon is less than an, which is at most L, which is certainly less than L plus epsilon. Equivalently, the absolute value of an minus L is less than epsilon. Therefore an converges to L. For a decreasing sequence bounded below, negative an is increasing and bounded above. Applying the result already proved shows that an converges to the infimum of its terms. This completes both halves of the theorem. We write an tends to positive infinity if, for every real number m, all sufficiently late terms are greater than m. Positive infinity is not a real number, and this is not convergence in the ordinary real sense. The notation records a particular kind of divergence. If an increasing sequence is unbounded above, then for every m, some term an exceeds m. Monotonicity then makes every later term exceed m as well. Hence the sequence tends to positive infinity. Similarly, a decreasing sequence unbounded below tends to negative infinity. A subsequence is obtained by choosing a strictly increasing sequence of indices n1, n2, n3, and so on. The resulting sequence is ank. We may skip as many terms as we want, but we must preserve their original order. Rearranging terms is a different operation. Analysis is fussy about this because, occasionally, being fussy prevents false theorems. For an equal to negative 1 to the power n, the even-indexed subsequence is constantly 1. The odd-indexed subsequence is constantly negative 1. The original sequence therefore contains two incompatible long-term behaviors. Every subsequence of a convergent sequence converges to the same limit. To prove it, Fix epsilon greater than 0. Since an converges to L, there is an n after which every term is within epsilon of L. Because the indices are strictly increasing positive integers, nk is at least k. Therefore, if k is at least n, then nk is also at least n. So ank is within epsilon of L. The subsequence converges to L. Consequently, if two subsequences converge to different limits, the original sequence diverges. Otherwise, the original sequence would have a limit, and both subsequences would have to share it, contradicting uniqueness of limits. This test proves divergence, but its converse is false. A divergent sequence need not have two convergent subsequences. For example, an equals n diverges to positive infinity, and every subsequence is still unbounded. A useful structural theorem says that every real sequence has a monotone subsequence. The sequence itself may oscillate chaotically. Somewhere inside it, order is still hiding, presumably to avoid doing anything useful until selected. Call an index n a peak if an is at least every term that comes after it. There are exactly two possibilities: infinitely many peak indices, or only finitely many. This is the sort of exhaustive case split analysts dream about. If there are infinitely many peaks, list them in increasing order as n1, n2, n3, and so on. Each chosen term is at least every later term, including the next chosen one. Thus these terms form a decreasing subsequence. If there are only finitely many peaks, choose n1 after the last peak. It is not a peak, so some later term is larger. Choose such an index as n2. That new index is also after the last peak, so it is not a peak either. Repeat indefinitely. This constructs a strictly increasing subsequence. In either case, a monotone subsequence exists. To summarize, a monotone sequence converges exactly when it is bounded in the direction in which it moves. Subsequences preserve an existing limit, and incompatible subsequential limits prove divergence. Finally, every real sequence contains a monotone subsequence. That quiet fact will make bounded sequences much less mysterious. That is all for B3. Order has been found, and chaos has merely been postponed.